Hello everyone, welcome to IDEA StatiCa webinar. Usually on Wednesdays we run our Connection Wednesdays webinar, but this time we decided to use this date to introduce our very new application, IDEA StatiCa Member. So you can meet it and find out what it can bring to your professional workflow. My name is Jana Kadirova. I'm a product engineer at IDEA StatiCa. I will speak about the application in more general way, and my colleague Vít Hurčík will show you one practical example in the application.
Hello to everybody.
As usual, before we start, please note that you can communicate with us via the questions panel in GoToWebinar, so feel free to send us any questions. We will try to answer them during the webinar. So just a brief introduction of our company. We in IDEA StatiCa are a company with 30 years experience of making software for structural engineers. We have thousands of users around the world in more than 70 countries. Our results are validated by universities. We are connected to many other softwares that you use, and we are mainly focused on structural design and code check of joints, cross sections, and other structural details. Generally, most of the softwares that engineers use are focused on the structure as a whole. So they model the whole structure. But the majority of defects turned out to be caused by a bad design of a particular detail or due to some buckling issues. So the engineers have many very great tools to use in their everyday practice. Probably each of you have some of these softwares or maybe some other software. But there are still some issues that are difficult to cover by only these softwares. In the first row, the connection design, and also the buckling issues. And that's what IDEA StatiCa decided to focus on. We offer engineers our application IDEA StatiCa Connection for checking steel connections of basically any topology. And now, to solve the buckling issues, we introduce our new application IDEA StatiCa Member. Again, you are not limited by some topology requirements. You can model a structural member of any shape. IDEA StatiCa Member is still in a beta version, and as I mentioned, it's dedicated to analyze and check the buckling of steel members. It means some beams, columns, diagonals, etc. You will see in this presentation. Now I will just switch off the camera and I will start speaking about the application. So during the development process, we try to investigate the workflow of engineers. How do they check a structural member? And basically, we can separate the check into two stages. In the first stage, the engineer has to check some cross sections, usually some most loaded ones or the most dangerous ones. And after, they continue to look at the structure or at the member as a unit, and they have to solve the buckling issues. Engineers use the relations that are defined by some national design standards, and in the same way, you can use the IDEA StatiCa Member for the check of, let's say, the cross section, or you can use the standard analysis, which can display the strain and the stress. It uses the nonlinear material, so we call it materially nonlinear analysis, and we limit the plastic deformation based on the national standard, basically with 5% of plastic strain. Once we want to check the buckling issues, we need to see the eigenshapes and the corresponding critical force factors. And once we have this information, which we get from the linear buckling analysis, we can decide which eigenshapes are the dangerous ones for the structural member, and we will apply some imperfection on these eigenshapes. With such a loaded model, we continue and run the geometrically and materially nonlinear analysis with imperfections. And again, we will get the picture of stress, of strain, and we limit the strain by 5%. Let's have a look at how is the workflow in the application. So first of all, we need to have the analyzed global model in some, let's say, big software. So we have the structural as a whole. We have some structural member which we are not sure if the buckling analysis within the global analysis is enough, and we want to analyze it in a detailed way. So we take this structural member from the global model, we cut it and model it within IDEA StatiCa Member together with the related members. The related members are marked with the 1D as 1D elements in this figure. On these related members, we apply the corresponding boundary conditions so that the piece of the structure behaves in the same way as it would do in the global model. In the next phase, we need to load the member. We can load the analyzed member as well as the related members. Again, we need to check the equilibrium condition as usually. Now we can continue and model the connection between the analyzed and the related members. If you know IDEA StatiCa connection application, so the workflow is just the same. The user interface opens and you can use all the manufacturing operations that you know from connection application. You will model the join, the connection, and also what is possible here is to add another operations along the member. So you can add some openings, stiffeners, cuts, etc. And that's it. We have the completed model and we can continue and analyze it. Behind the user interface, there is the well-known component-based finite element method, CBFEM, which you already know from IDEA StatiCa connection. But this method is recognized also by other applications, other softwares like Process Engineering by Hilti, Advanced Design Connection by Greytech, or Westalpine Profile Form. So everywhere in these softwares is this method implemented. As I mentioned in the beginning, you will find 3 different analyses in IDEA StatiCa Member. I will not speak about them again because I already introduced them. I will just show you how you can use them in a practical example. So we can have a look at such a, let's say, simple member. It's a bent beam loaded by some concentrated forces. And in the first stage, in the stage of the check of the, let's say, section, we will run the materially nonlinear analysis. All the member is meshed and the CBFEM model is created. All the bolts, welds, contacts are there, and we will analyze the stress and strain. We will check the plastic strain, which is limited by 5%. We can continue and start the buckling check. Therefore, we will run the linear buckling analysis first, which gives us the first several eigenshapes and corresponding factors. In this example, you can see the first eigenshape on the left and the second eigenshape on the right. You can see that the first shape corresponds to some lateral torsional buckling of the top flange, and the shape is of a 1/2 wave. The second shape is the full wave. Now we have to decide which of these eigenshapes are the most dangerous ones. In this example, we decided that we will use the first shape, and we applied 13 millimeters imperfection on this shape. The value is not random. It's calculated based on the formulas you will find in the national standard. And with such a loaded model, we will run the third analysis, which is the geometrically and materially nonlinear analysis with imperfections. And the result of it is, again, the picture of stress, of strain, and the check of the plastic strain. I have one more simple example. It's a column loaded by compressive force, and it's just the same. In the first step, we will run the materially nonlinear analysis. We have the stress and strain picture. From the literal buckling analysis, we will get first several eigenshapes, and in this example you can see that the first one on the left and the second one on the right have the factors which are quite close to each other. Therefore, in the third step, or in the third analysis, we will apply the imperfection on both of these eigenshapes. And for each of them, we can use a separate value. And this is something which is not really possible with the standard check, but you can get results from it using IDEA StatiCa Member. And of course, you can use this application on more complicated cases. For example, this is a castellated beam with circular openings. There are some cleat connections, and you can see that the bracing, which is located in approximately 1/3 of the span, has a big influence of the eigenshape. Or you can see such a secondary beam connected to primary beams by shifted end plates. Again, we can model the connection as it looks in reality, and we can analyze the influence of the beams. Last example is such a simple frame with inclined column. It's anchored to concrete blocks, and it's braced or supported in one of its corners. And you can see that such a Such a frame will be sensitive to lateral torsional buckling of its non-braced corner. Before you start using the member application, we thought that it's really important to mention several things that each engineer should know, because as usual, software is it's not a magic box that will give you all the information, or it will not do the engineering job for you. The engineers still have the responsibility. So it's important to emphasize some things. First is that the engineer should be familiar how to input the imperfection into the global model. So usually you put some value of imperfections into your global model and you analyze the whole structure. You have some critical factor, and based on the value, you can decide whether some member, whether you need to check the backlink issues for some member, or you don't have to. When the value is quite high, maybe the engineer decides that he doesn't need to check the backlink issues. But for the lower values of the critical factor, it would be good to analyze it in a more detailed way. And now he can go to IDEA StatiCa Member and model it there and get more detailed information about the eigenshapes, and the engineer can decide whether or which shape is the dangerous one, and he can also put imperfections on that. What is also important to mention is that we check the analyzed member as a whole, and we do not check the connections. The connections must be designed and check somewhere else, probably in IDEA StatiCa Connection, or you can use some other tool for that. But you have to input the correct load for the check of the connection, and it could be different, maybe different combination of load that you would use for the member check. The member can model the real stiffness of the connection, so it's something that you will not get from the global model. And you know that the connection has a big influence on the eigenshapes of the member. And the last thing, I already mentioned it before, but I will tell it once more. This application is still a beta version, and the verification process still runs, and we are working on how to give engineers another studies and comparison of the model. Sorry. But what can IDEA StatiCa Member provide to engineers is the better understanding what is really happening in the beam. So it can give you more real picture of the behavior. And these are the examples that I already showed you before, and you can use the application on much wider range of members, maybe quite complicated ones. So now I would like to stop speaking, and I would pass the word to Vít, who will finally show you the application and the workflow on an example. So the floor is yours, Vít.
Thank you, Anna, for the great presentation. And we will jump right into the application. I will start with the wizard because I want to create a new project. So let's just type in a bridge segment, and because we will design the bridge segment, design and call check. to be specific. I will just only let here steel grade, and I will choose the geometry to be beam and change the span because I want to have a span of my beam 4 meters. Great. I will start with this design and I will follow the tree of the entities. Let's change the properties of the analyst member. This is the member which we are interested in. And we will design the welded cross-section, quite a high, slender welded beam. With thickness of the web 14 millimeters. Right, it's right there. From the global model, I already know that that this beam is set in Z offset 100 millimeters down, and I want to keep that geometry. I don't like these related members, so I will just delete them. And I will add a new continuous members in Y direction because I want my main beams of the bridge. So let's add one here and one here. And now I will change the cross section because I really want to have steel welded box cross section. So 1200 thickness of the flange 300 millimeters, width 800. The same thing for the bottom flange. Thickness of the web will be 16 millimeters and inner distance 600. Right now I designed the main beam cross section. And I want to define the geometry because this is the segment of the larger beam, structure of the bridge, and I have the segment cut off from the structure. I will design the geometry as 2 meters from one side and 2 meters from the other side. So this segment length is 4 meters. And we must define the boundary conditions also. So I will check the rotation in x-axis. And let's define the same thing for the other main beam. We already did this. So -2 and 2 meters. And also the same boundary conditions. I designed the boundary conditions with the respect of the boundary conditions to global model, which I did in a previous step. Right now, I can continue with the connections. As you already know, we need to design the connections between analyzed member and main members or the related members. And this will be done in the IDEA StatiCa connection UI, user interface. And give me just a second, it opens in other screen, so I will just put it here. I will add only one operation, cut, because I want to weld these beams together. Okay, I will cut it by surface, and this is the way how I want it. Just saving, close the window, and you can see right there our connection is designed and the related member and analyzed member is connected. I want to have the same thing on the other side, and I don't want to design it again, so I can apply the same recent connection what I did to the other side. Great, and this is our bridge segment. Right now we will need to define the loads. So here in loads, I will add line load because I want to have two separate loads. So from 1.3 to 1.7 meters minus 6,000 kilonewton meters per 100 meters on the top flange. And again, on the other side, in a symmetrical way, 2.3 and 2.7 minus 6,000 on the top flange with width 100 millimeters. Great, here we have it. And because this is a segment cut it from the global structure, we need to add end forces on related members to maintain the equilibrium of the section. So I will add also here bending moment, which I know from the global structure. Great. I loaded our members. Right now, I can add some manufacturing operations. For example, I really want to have here stiffeners because I want stiffen the main transversal beam to bear the loading. Okay, let's move it to this position and I will repeat it with a count of 2 in 300 millimeters, just creating the copy and designing the stiffness for the second load. Okay, now I'm done. We designed our analyzed member and we can proceed to check. I just start the materially nonlinear analysis, and which is the first key to all analysis. We need to do this as a first step because other analysis needs the results of the first one. This one, the first one, is the most simple one, and it will take only a couple of seconds. Great, we have the results. As you can see, we have strain on plates, we can see the stress, deformations in 3 directions, and a lot of other interesting stuff. But this is only the first step. The most important are the second and third. And right now I will start the linear buckling analysis. And right now we will have to wait a little bit more.
Okay, maybe Vityo, you can use the time to show some documentation which we already prepared for users.
Oh, that's a great idea. You already know that we are giving you a lot of information in the resources. So if you go to Resource Center from our homepage, here is prepared for you a brand new topic member with tutorials. We prepared 3: a simple beam for the beginners, bridge segment, and the frame. We prepared frequently asked questions, which we will definitely improve in the future. We have sample projects for you, 1 video, theoretical background, which is very interesting. You can see or read there how it works in the basis. So visit our resource center. Meanwhile, we have results of a linear buckling analysis. We have our eigenshapes. I will turn the deformation view in Y direction because in this view we can see better what is going on here. In the first buckling shape, we can see that we have here two things. First one is the lateral torsional buckling of the transversal beam. And second effect is the local buckling of the slender beam due to the shear stresses. And the second buckling shape, we have only the local buckling of the slender plate due to the shear stresses. In the third eigenvalue shape, we have the same thing. In the fourth, with the same factor, is the same, but with a different side. At the fifth buckling shape, we have the only lateral torsion stability loss for the transversal beam alone. And in the sixth shape, we have loss of the stability of the wall of the main beams. And this is not important for us right now because we are examining the behavior of the transversal beam. This effect should be taken care of in the global analysis before. So right now I'm deciding that the most extreme for me is the first buckling shape. And with this decision, I can go on to last analysis, and I will type in here value of the imperfection, and I can start the analysis. I will have for you a really small presentation, just 4 or 5 slides, in which I will show you how I decided and how I calculate the imperfections. First, our transversal beam is a welded cross-section, and with its parameters I can calculate the imperfections because the code tells us which buckling curve must be used and how to calculate the value of bow imperfection. And with the length of the beam, I can calculate 20 millimeters. But for the lateral torsional buckling, there is a recommendation to reduce the value with K factor. So I will multiply it, and I have 10 millimeters finally. And for the second effect, for the imperfection of the slender member plate, for local buckling, we have different code with different approach. And here I have calculated this number. What is the most extreme one? Definitely the higher one, the 10 millimeters for the lateral torsional effect. But we have these two effects in one buckling shapes, and I want to have 10 millimeters here. So I need to scale the value for this imperfection. Right now, I will show you the results of the final analysis. You can see that with imperfection 11 millimeters, the geometrical, material, and nonlinear analysis with imperfections didn't finish the calculation. It didn't apply 100% of the loading because the mathematical process didn't converge to the end. The analyzed member loses the stability, and we can basically say that it didn't pass the code check. It loses the stability in lateral torsion effect. How to avoid that? Well, you can make some changes. For example, you can go back to design and design the stiffeners in a different way. For example, make them inclined. I prepared for you another example, and I calculated already in advance. And in this example, I prepared the stiffeners in this way. I make them a little bit inclined, and with this design, I achieved more stiff. The member is more stiff, and the member passes the code check. So in this example, IDEA StatiCa Member helps me to design the slender high beam as a transversal beam in bridge. And this is the end of my example, and I will pass the word to Jana again.
Okay, great, Vitya. Let me sorry. Okay. So thank you for the example. Let me just tell you how you can get the application, because you are already asking about that. So the beta version, it's available within the 10.1 setup, which we released in October. So if you did not upgrade your setup, you can do it now, and you will find there a new icon, IDEA StatiCa Member. The application is free for all users who have the Steel license. So if you have any license for Steel products, you can also use the member. And because we want to get in touch with users who try the application, we ask you to register. It's only the first time you use the application. You will just fill in your name and email, and probably we will send you some application to some with some questionnaire. How did you like the application? If you had any problems with that. We also collect the feedback for all users so that we can implement some new improvements for the version 20, which is planned to be released in April next year, 2020. So we will skip from version 10 to version 20. And in that new version, there will be also BIM links to other softwares. Somebody also asked about that, if it's possible to export the member from other application. So yes, we are working on that. It will be available in version 20. And we need to hear your voice. We need to know if you like the application, if you think it can be useful for you. So you can find special page for IDEA StatiCa Member on our web under the Steel tab, and in the very bottom there is a button for the survey of users. So we kindly ask you to give us some of your precious time and fill the survey. And that's basically the very end of the webinar. As usual, after the webinar is closed, you will be asked to fill a very short survey, how you like the webinar. If you want to see something special next time, we will send you the link to the recording of the webinar. It will be available on our webinar web, on our website, and also on our YouTube channel. If you still don't have the IDEA StatiCa application, you can get the free trial for 14 days also on our website. And of course, the resource center is full of documentation, full of materials that can be helpful for you. Next week, you can look forward to meet with our colleague Orsi, who will show some examples of precast beams. So it will be dedicated to concrete structures. And of course, in next 14 days, you will meet Adam and David, our two colleagues, in another Connection Wednesday that will be focused on a correct model. So probably you will find out some very useful information how to build a correct model. So we invite you to register for webinars. It's for free, and you can find the forms on our website. That is really the last thing I wanted to tell you. So once more, thank you very much for your time. We really appreciate that such a big audience is regularly coming to our webinars, and we wish you to have a beautiful autumn day. Goodbye.
Have a nice day.